Have you ever watched a leaf just kind of flutter to the ground while a little rock you dropped at the same time has already hit the pavement? It makes you think you know exactly how gravity works, right? Heavier things just fall faster. But what if I told you that what we see every day is actually hiding this beautiful fundamental truth about how the universe really operates? Today, let's dive in and take apart one of the biggest misconceptions in all of physics.
Okay, so let's start with a really simple, direct question. Just imagine you're standing on top of a tall building. In one hand, you've got a heavy bowling ball, and in the other, you've got a light, fluffy feather. You let them go at the exact same time. Which one do you think is going to hit the ground first? Seriously, just go with your gut.
And yeah, of course, your intuition is screaming that the bowling ball wins, and you'd be totally right. Here on Earth, in our world, that bowling ball is going to smack the ground while the feather is still sort of gracefully floating its way down. So the thing is, your observation is spot on. But the reason why that happens, well, that's where it all gets really interesting. See, the reason our intuition feels right, but is also kind of wrong, comes down to one single invisible thing that's all around us all the time: the air. Yep, this invisible ocean that we walk through every single day, that's the real culprit making the feather lose the race.
You can think of it like a tug of war. For any object that's falling, you've got gravity pulling it down, and that pull is based on the object's mass. But at the exact same time, you have air resistance, or drag, pushing up against it, and that force depends on the object's shape and how fast it's going. A bowling ball, it's dense, it's aerodynamic, it just slices right through the air. But a feather, with its huge surface area and almost no mass, it catches the air like a tiny parachute. And that's why air resistance messes with the feather so much more, slowing it way down.
So this leads us to the big question, the thought experiment that physicists just love. What if we could just get rid of the air? What if we could stage a perfect, fair race between the bowling ball and the feather, with nothing getting in the way? What do you think happens then?
Because once you take the air out of the equation, you finally get to see gravity for what it truly is: a simple, elegant, and totally constant rule that applies to everything, everywhere.
And this is it. In physics, we call it gravitational acceleration, or just little g. Now, the key words here, the ones you absolutely have to remember, are that all objects accelerate at a constant rate regardless of their mass. That's the whole game right there. In a vacuum, the universe just doesn't care if something is a feather or a bowling ball. It's going to accelerate them both at the exact same rate.
And here on Earth, that constant has a number. This is the magic number for anyone studying physics: 9.8 meters per second squared. Okay, so what does that actually mean in plain English? It means that for every single second an object is falling freely, its speed going down increases by 9.8 meters per second. So after 1 second, it's going 9.8, after 2 seconds, it's at 19.6, and on it goes. And this is true for everything.
So why? Why does this happen? It feels so backwards, right? Well, think about it this way. It's true that gravity pulls with more force on a heavier object, like our bowling ball. But that extra mass also gives the object more inertia, which is really just a fancy way of saying it's harder to get it to change its motion. So you have a stronger pull, but it's also harder to move. And it just so happens, in this beautiful bit of cosmic coincidence, that those two effects, the stronger pull of gravity and the greater resistance to moving, they cancel each other out perfectly. And the result? Everything accelerates at the exact same rate.
Now, this is all fantastic in theory, right? It sounds great on a whiteboard. But for scientists, theory isn't enough. You need proof. For hundreds of years, this was just an idea, a thought experiment. But then, in 1971, we found the most perfect laboratory you could ever imagine to put this whole idea to the ultimate test. And this experiment wasn't just some random thing they decided to do. No, this was the grand finale of a scientific question that was over 400 years old. It all started way back with Galileo, who was the first to really propose that objects should fall at the same rate. And it all came to a head on July 31st, 1971, with the crew of Apollo 15.
Just try to picture this scene. You are standing on the surface of the moon. There's no air, no wind, nothing. It's a near-perfect vacuum. And Commander David Scott is standing there. In one hand, he's holding a geological hammer. In the other, a falcon feather. He was literally about to perform Galileo's 400-year-old thought experiment for the entire world to see.
He held them out, and he dropped them. And as they fell, perfectly side by side, he said these now famous words. It was such a simple, human moment, But it was also this profound act of scientific validation, connecting a thought from the 1600s to a physical reality in the 20th century.
And the result was just beautiful. The hammer and the feather, one made of heavy metal, the other a delicate piece of a bird, they fell at the exact same rate. They hit the gray lunar dust at the exact same instant. It was perfect, undeniable proof. In a vacuum, mass just doesn't matter. Gravity is the great equalizer.
So, okay, why do we care so much about this? For anyone studying physics, understanding that g is constant isn't just a cool piece of trivia, it's everything. It's the bedrock, the fundamental assumption you need for almost every problem in kinematics. When you're trying to calculate the arc of a thrown baseball, or the path of a rocket, or even the orbit of a satellite, it all starts with this one single principle. Gravity accelerates everything equally.
So, that leaves us with one final, nagging question, doesn't it? We know the astronauts on the International Space Station are still very much in Earth's gravitational field, and we know that gravity makes everything fall at the same rate. So, why do they float? Well, that's a puzzle for another time, but figuring that out is the next giant leap in understanding how gravity really works. Thanks for digging into this with me.